Hello. In this section, we will cover the first half of modeling with first order equations. In particular, we're going to look at mixing problems. Mixing problems are a classic application of first order differential equations. To get us started, let's look at a problem where we have a tank initially contains Q0 pounds of salt dissolved in 100 gallons of water. We also assume that water containing ¼ pound per gallon of salt enters the tank. At R gallons per minute. In addition, we assume the well-stirred mixture that's in the tank is drained from the tank at the same rate. And our goal is to go through and find the amount of salt at any time. Okay, so to get us started, right? So first, let's make sure that we kind of understand what's going on here. So it's asked us to go through and find the Q of t at any time. So what we're looking for is we're looking for the function where we would plug in a time value and out would come the amount of salt. Okay, so let's think about that. So if Q of t is the amount of salt at any time, then dq dt would be the rate of change of the salt. Okay, so that's going to give us a formula, a function, where if we went through and plugged in a time value, we would find out how the salt is changing at that particular instant in time. Okay, so let's go through and try and create an equation for that and see if we can put something together. Okay, so if we're looking at the rate of change of salt, like dq dt, then the most important thing is to go through and know what you're looking for, right? So in the numerator here, this is the change in salt, okay? This is an instantaneous rate of change, but we still have a change in salt in the numerator. So what we're looking for is we're looking for a quantity of salt to be in the numerator. And salt in this problem is in terms of pounds. So we're looking for it to have pounds of salt in the numerator for our rate of change. And for our denominator, we have time. And the time that's given, if you look back at the information they gave you, is minutes. So we're looking for something that has minutes in the numerator. Okay, so let's see if we can go through and figure out how to take the information that's in this problem and structure it into an equation for dq dt. Okay, so what have they told us about the way that the salt is changing? Okay, so if you read this first sentence, a tank initially contains, this is dealing with the starting point. It's not telling us anything about how the salt is changing. Okay, meanwhile, if you read the second piece of information, water containing 1/4 pounds per gallon of salt is entering the tank at a rate of R gallons per minute. So that is going to change the amount of salt that's in, right? So if you've got a liquid that's entering the tank that has salt in it, that's going to change the amount of salt that you have in the tank. And so that's going to be part of the rate that the salt is changing at. And what you could do is you could go through and just try and just take this information and just write it down in here, right? So this is entering in. So actually, hold on, let's do one thing. So the way that these problems are typically structured is you do the rate that the salt is coming in minus the rate that the salt is going out. So that might make things easier. And so let's look at the rate that it's coming in. That's what we were just going over. If you just go ahead and write 1/4, so this sometimes can be helpful, is just to go ahead and write down the amount that they've given you. Okay, so that's still going to be dq dt, and we still want pounds in the numerator, and we still want minutes in the denominator. So let's take a look. If you just take the 1/4 pounds per gallon they gave us, is that, do we have pounds over minutes? Well, let's look. We have pounds over gallons. Okay, that doesn't work. We need to have pounds over minutes. So that tells us that we need to go through and multiply by something to convert this pounds per gallon into pounds per minute. And ideally, that thing that we would multiply by would have gallons over minutes, because we want to go through and convert this pounds per gallon into pounds per minute. And so we need to cancel the gallons that's in the denominator and introduce a minute that's in the denominator. Okay, so if you go through and just kind of keep reading here, we've got 1/4 pound per gallon enters a tank of R gallons per minute. Well, what do we want? What we want gallons per minute. So if you go through and put R in here, then the combination of this, all right, will end up producing pounds over minutes, which is what we need to have for our rate of change. And so if we were to go through and multiply these two, we'd get R over 4 pounds of salt are going to be entering the tank per minute, right? Does that make sense? So the way that to think about it is that this is the concentration of this is how concentrated the salt is that's coming in. That's not going to be enough information to tell us how much salt is going in, because you could have that concentration. You could have only a little coming in, or you could have a lot coming in, and the difference between those is going to change how much actual salt enters the tank. Okay, and so that's the type of calculation that you need to do on these mixing problems. Is you need to go through and take concentration and take rate and combine them to get the rate of salt, right? Concentration and then rate of the liquid, and then combine them to get the the rate of the salt. Okay. All right. So let's do the second part, minus the rate out. And to go through and figure out the second part, it's frequently valuable to think about how you did the calculations for the first part, right? So we had 1 pound per gallon, and then we multiplied by R gallons per minute. So if we could do something similar where we had something pounds per gallon and multiply by something gallons per minute, that frequently ends up being the way that these problems end up working out. That's just the easiest way to do them. And so let's think about that for a second. So the the gallons per minute part actually is the easier part of this. If you go through and read the next part, the next part gets into the rate out. The well-stirred mixture in the tank is drained at the same rate, the same rate. All right, so this tells us the rate that the mixture is leaving the tank is also going to be R gallons per minute. And so the only thing left to go through and figure out is what is the concentration that is in the tank as it leaves, as the well stirred mixture is drained from the tank. And the way to go through and figure that out is we need to know how many pounds of salt are in the tank and how many gallons are in the tank, right? If you think about it, we've got a tank that contains um, this mixture, right? And we want to know, well, if it's being drained and we want to know the concentration that's being drained, well, the concentration is how many total pounds of salt are in the tank at that time, and then how many total gallons there are at that time, right? Does that make sense? And so if you go through and figure that out, right? So how many pounds of salt are there going to be? Well, if you read this, we know that Q of T is supposed to represent the amount of salt at any time. So Q of T is going to be the total amount of salt that's in the tank at that time. And then gallons, we've got 100 gallons in the tank. And so if you combine the function that you're trying to find, which has the salt at any time, that will be the amount of salt that's in the tank at any time. And if you combine the total amount of water, that will be the total gallons. And so we end up combining them to get the concentration. Okay. And then so at this point, you can go through, you can cancel the gallons here. And if we simplify this and just drop off the units, we get R over 4 minus R times Q over 100. And the result here is a differential equation, a first order differential equation that we can go through and we can solve. So let's do that on the next page. Okay, so how could we go through and solve this? Well, one thing to keep in mind here is that the R is given. It's going to be a constant. And so effectively what we have is we have an equation where we have a constant minus the function we're trying to find times another constant. If you recall from an earlier video, we solved problems that have this structure. All right, so in particular, they would be problems that have the structure AY minus B. Okay, so if you have dy dt equals ay minus b, that's the same structure as this. I realize that it might not look like it because the r is kind of disguising it, but the r is a constant, and so r over 4 is going to be a constant, and r over 100 is going to be a constant, and so we have the same structure as a constant times the variable minus another constant. Okay, so when we solved this, what did we end up getting? We went through and said that the formula for this is going to be b over a plus ce to the at. That's what we end up getting when we go through and solve differential equations that have this structure. This is a formula that we derived in an earlier video. Okay, so we just want to go through and use that. So to use it, we could rewrite this so that it looks more like that. So we could we could switch these around and have negative R over 100 Q plus R over 4. And now it looks a little bit more, right? So this would be A. This would be, well, see, the formula has a minus B, so we're going to want B to equal negative R over 4, right? And then A would equal negative R over 100. And then we can jump right to the solution here. So Q is going to equal, so the way that you do it is you take your B and you divide by A. So we're going to take B, right, which is negative R over 4, and divide by A, which is negative R over 100, plus CE to the A, which is negative R over 100 again, times t. And if you simplify that, right, you could flip and multiply this, and we'll end up getting 25 plus CE to the negative R over 100T. Okay, so that is going to be, that's the solution to the differential equation. However, we do have more information here that we could combine into this. We could actually go through and solve for C, because if you look back at this problem, they did give us an initial condition, right? So if you look at everything that we've used, we used the rate in from this sentence here. We used the rate out from this sentence. In a way that we used the sentence, right? That told us that Q was the amount of salt at any time. We have not gone through and used the fact that the tank initially contains Q naught pounds of salt. So the Q naught pounds of salt, what this is saying is that if we went through and did Q of 0, right? If Q of T is the amount of salt at any time, then Q of 0 would be the initial amount. That would equal Q naught. So we can go through and use that fact to solve for C, right? So if you take Q of 0 and plug it in here, we're going to get 25 plus C. And then if you put a 0, right, we're going to end up with 0. E to the 0 is just 1 times 1. And then so we'll have Q naught equals 25 plus C. And then Q naught minus 25 equals C. And putting those, taking that and substituting back into our earlier equation, we'll end up with Q of T equals 25 plus Q naught minus 25 times E to the negative R over 100T. And that's the solution, right? So at least so far. Okay, so if that were the only, those were the only questions, that was the only goal of the problem, then we would be done. Okay, so if they give you a problem that looks like this, and it just has these 4 parts, you have got an initial condition, you've got some quantity coming in, you've got a quantity going out, and they ask you to find the quantity at any time, then this is the way that you go through and do a mixing problem. Is you start off by doing rate in minus rate out. Frequently, those rates turn into a concentration times the rate that the liquid is coming in, and you combine those to get the rate that the quantity is coming in. And then you do the same thing for the rate out. You end up with concentration times the rate that it's leaving at. And then you just end up multiplying and canceling the units. Okay. And then once you've done that, you can then go through and solve the differential equation using methods that we've derived previously. So for example, this formula that we derived back in an earlier video. Okay, so this problem has additional questions, more parts that we can go through and answer. So these might be potential questions that you might encounter on other problems that are similar to this. And so, I wanted to go through and answer all of these types of questions just, at the very beginning to show you how to do all these different cases. So let's go to the next page, and we're going to copy this formula, this function that we've created, and then we can answer some questions about it. All right, so we've got Q of T equals 25. All right, so here's a potential question that you could be asked. Find the limiting amount of salt that would be in the tank after a long time. Okay, so if we have a function that gives us the amount of salt at any time, and we're asked to go through and find the amount of salt after a very long time, then the way that you would handle that is to take the limit as the time goes to infinity. So then we're going to get the limit as t goes to infinity, 25 plus q naught minus 25 e to the negative r over 100t. If t goes to infinity, oh, that's a very odd looking r. If t goes to infinity, then we're going to get a very large negative exponent, right, here. And then e to a very large negative exponent is going to go to 0. So this goes to 0. And then we'll have something times 0. That's going to be 0. And so you'll end up getting 25. Okay, so the way to go through and find the limiting amount is to take the limit as the amount of salt, or sorry, as the amount of time goes to infinity. And as you can see here, right, so you just end up getting this quantity here. Now, that assumes you have a negative exponent, but you're going to end up getting that quantity there. All right, what's another potential question that you could be asked? In this case, we left some unknowns, so we didn't specify what R was or what Q naught would be. So let's go through and specify those and then just kind of play around with this. All right, so if R equals 3 and Q naught, oh, whoop. One thing that I forgot to mention in this previous problem, right, is that this quantity, right, this is going to be the amount of, this is another name for this is the limiting amount. And we're going to go through and give that a name. So we're going to say that is QL, right? L for limiting amount. And so the QL is going to be 25 because we're going to use QL right now. All right, so we're going to do 2, Q naught is 2 times QL. Find the time when the salt is within 2%. Okay, so here's a potential question that you could be asked. If we're saying that the rate is 3, so 3, right, that looks a little strange there. But if you go back to the original problem, we did specify units in the original problem. So we're talking about 3 gallons per minute. So if the rate is 3 gallons per minute, and the initial amount of salt, right? Remember that Q naught is the initial amount of salt. If it's double the limiting amount of salt, the amount that you'd have after a very long time, find out how long it will take before the amount of salt in the tank is within 2% of the limiting amount, right? So, you know, you can read into this that we're saying that Q naught is if QL is 25, then Q naught is going to be 50. So if we start with 50 pounds of salt, then when are we going to be within 2% of 25 pounds of salt? Does that make sense, right? So we're going to start off at 50. The amount of salt is going to decline over time. Okay. The way you can tell it's going to decline is that negative, by the way, that negative exponent tells you that you're going to have a decline in the value of your quantity. And we want to see how long it takes to decline from 50 to within 2% of 25. Okay, so how could we go through and figure that out? Well, let's just review briefly like how this function works. Okay, so there's 2 different things that you can accomplish with a function of this type. All right, you could plug in a time, and if you plugged in a time into the function, it will produce the quantity of salt at that time. Okay, but another thing that you can do with the function is you could plug in an amount of salt, right? If you plugged in an amount of salt here, like if I plugged in, you know, 30 pounds of salt, I put 30 here, then I would have an equation here where t is the unknown and I could solve for time. So you can plug in the quantity of salt and then find the time. So it goes both ways. You can plug in time and find quantity, or you can plug in quantity of salt and find time. And so the second of these two is what it's asking us to do. So we need to go through and figure out, we need to plug something in, some quantity over here, and then we'll have 25 plus, and then we're saying, so Q naught is going to be 50, so we could pop that in. and R is going to be 3. So we can pop that in. And we need to figure out what do we put here. Okay. And what that's going to be is it's going to be a quantity of salt, right? So we want to plug in the quantity of salt that is within 2% of the limiting quantity. So how could you find that? All right. Well, what you could do, right, is you could start off by just taking 2% and multiplying it by the limiting amount. Okay. So if you do that, you get 0.02 times 25, and you'll get 0.5. Okay, so should we put 0.5 here? No. Okay, so the issue here is that this is 2% of QL, right? That's not within 2%. So to find when we're within 2%, you need to take that quantity and add it to QL. Okay, so within 2% of 25 would be actually it would be either 24.5 or 25.5. So 2% below the amount would be 24.5, and 22% above would be 25.5. Now, contextually, you can tell which one you should use, right? If you start off with 50 and the amount of salt is decreasing over time, and you're asked, how long does it take before it decreases to be within 2% of 25? Well, then we're going to use the bottom one, okay? Now, contextually, a different problem might ask you to get within 2%, and you might use the 24.5. So you need to look for context here, but we want to put 25.5 here. Once you've done that, from there, this is just an algebra problem. So let's go through and solve our algebra problem, right? So move the 25 over, so 0.5, 50 minus 25, we get 25. And then we can divide over the 25. And as we noted earlier, 0.5 divided by 25 is 2%, right? So we're going to get 0.02 equals e to the negative 3 over 100t, and then take the natural log of both sides. The natural log and the e cancel, and then divide or multiply by the reciprocal, and we get t equals negative 100 over 3 times the natural log of 0.02. And if you pop that into a calculator, you'll get that that is approximately 130.4. Okay, and so what is t in terms of? So we should put units here. So if you go back to the beginning, right? So what is our time? Our time is in minutes. So you can just pop in minutes. So that's a potential question where you've gone through and you have found your function, and then you're asked to go through and do something with your function. And this is just a particular thing that you could be asked to do with it, right? So you could be asked to find a quantity at a time. You could be asked to find a time that matches with a quantity, and the second of those two is what we were asked to do. And we were given some a little bit complicated information that we had to work out. Instead of just having the problem say, find the time when the quantity reaches 30 pounds of salt. Instead, they did this 2% of QL thing to just make it a little bit more complicated. Okay, let's go through and do one more thing with this problem. So another question that you could potentially be asked goes through and it says, find the rate required for the situation in the previous problem to be less than 45 minutes. Okay, so let's go ahead and take our let's glance at our previous problem here. So we went through and did this situation, and we got 130.4 minutes. And the instructions are what would the rate have to have been so that instead of getting 130.4 here, we would have gotten less than or equal to 45 minutes. Okay, so to go through and find that, what you want to do is you want to redo this problem, except we know what we're going to know what the time is, and instead the unknown is going to be the rate, right? So what was the rate? The rate was that R value, the 3 here. So if we can go through and take the 3 that's here, replace it with R, and then take the T and replace it with the time value. So they said less than or equal to 45 minutes. So we're going to use 45 as the maximum, right? That will tell us the maximum amount of time, give us the maximum amount of time. And the minimum rate that to achieve that. Okay, so let's try that. Okay, so we're going to have, we have Q of T equals 25. And then you can go ahead and just do the calculation here. It's 50 minus 25. So we're going to end up with 25. That's a funky looking 5. Let's try that again. E to the negative R over 100. And then we have 45 in there. And then we want to find the quantity when we get to, we want to find the time when the quantity will be 25.5. Okay, and you can go ahead and reduce the 45 over 100. And now we can just go through and solve for R. So subtract, we get 0.5. Divide, we get 0.02. And then natural log. And then multiply by the reciprocal. And then plug into a calculator. And you should get R is approximately 8.69. Okay, and this is a rate, so it should be in terms of gallons per minute. Okay. And there you go. So that is an example mixing problem. So we're going to go through and do a second example next, but I want to comment on this example before we move on. Right, so this is a classic type of mixing problem, and the steps that we went through to solve it are very typical. And so if you go through and try a similar problem, you just want to follow similar steps. One thing that you may see that can add a twist or a little bit of complexity to these problems is that you'll notice that we had water that was entering the tank at R gallons per minute, and the well-stirred mixture in the tank was drained at the same rate. I even underlined it here. All right, we got the same rate. What if the rates were different? Okay, so that is a potential problem that you may encounter. Okay, so just for instance here, if we went through and changed this and we said that the tank was being drained at R, or the liquid entering the tank was at R gallons per minute, and the tank was being drained at R minus 1 gallons per minute. Okay, then when you go to set this up, right, so obviously this will be R, and then this would be R minus 1. And you might think that that would be the end of it. However, okay, so this is just to be something to be aware of. If you do this, yes, the R here and the R minus one are both correct. However, but one other thing changes in the problem, okay? And that is going to be this quantity here, right? So what that is saying is that every minute, if you're adding R gallons and draining R minus 1 gallons, then you're adding an extra gallon every minute. And then, so if that were the case, you'd need to take this denominator here, and instead of having it be 100 gallons, well, you have 100 gallons initially, but after 1 minute you have 101, and after 2 minutes you have 102, and then 103 and 104. So what you need to do is you need to have 100 plus however many minutes have passed, to go through and determine the amount of gallons. Okay, so that this is the change that you'd have to make if you had this type of problem where you had R gallons and R minus 1 gallons per minute. So it's something to keep in mind when you're going through and solving mixing problems, is that if the rates differ, then it's not as simple as just putting the one quantity here and the other quantity here. For example, if this were 3 and this were 2, it's not as simple as putting 3 here and 2 here. You also have to adjust the number of gallons that you're using in your concentration for what's currently in the tank. Okay, so I hope that's helpful. All right, the next problem we're going to do is actually not going to involve that situation. It's going to involve another complexity, another potential twist that you could encounter. All right. So suppose a pond initially contains 10 million gallons of fresh water. Okay. Water containing an undesirable chemical flows into the pond at 5 million gallons per year. And the mixture that's in the pond flows out at the same rate. The concentration of the chemical that is entering the pond, right, the undesirable chemical, varies. And in particular, varies periodically. According to the function gamma of t equals 2 plus 2, not 2 plus sine 2t. grams per gallon. Find the amount of chemical in the pond at any time. Okay, so this is an interesting twist on the earlier problem. It's actually kind of a neat idea here, and that is that the concentration could vary over time. So we could end up having a function that where the concentration of what's coming in varies. So this could model, for example, you could have a river of some kind, and you have an industrial plant that's downriver, and the industrial plant, does some type of manufacturing at some part of the year, and when it does, it releases an undesirable chemical into the water, and so that would cause a periodic, addition of chemicals into the water, right? So it wouldn't be constant because the plant is not, maybe doing that part of the manufacturing process constantly. Instead, it does it, once a quarter or once a year. And so you could have some type of a function that could model, well, every June, chemical is pumped into the water. And so we could go ahead and include that in our solution and figure out how it would go through and change the problem. So it's a neat idea. All right, so in terms of how to solve this, we want to go through and use very similar steps to what we did in the first example. Okay, so the first thing we're going to do is we'll stick with the same letters, right? So we'll have Q of T be the amount of chemical at any time. Then dq dt will be the rate in minus the rate out. We know that we want the numerator, right? So the amount is in terms of grams. So we know that we want the numerator to be grams. And the denominator here is time. The time in the problem is given in years. Okay, so we want grams over years when we go through and substitute into this. Okay, so the rate in, to figure out what the rate in is, if we look at the first sentence, water containing an undesirable chemical flows into the pond at a rate of 5 million gallons per year. All right, so we're going to have 5 million. So we could have 5 times 10 to the 6th gallons per year. All right, and then here we're going to put, so this is right, if we look, we want grams per year, we have gallons per year, so we need something to put here that's in terms of grams per gallon, and then minus, and then we're going to have to figure out the same thing over here. We have, grams per gallon, and then we're told that the mixture flows out of the pond at the same rate. So we also get 5 times 10 to the 6th gallons per year. Okay, so this is one way that you could set these problems up, is to try and follow steps that are similar to the ones we did the first time, where we have concentration times rate, concentration times rate. And so in this case, they just gave us the rates first. And so we just put the rate, just go ahead and just pop the rates in there, and then you could find the concentration second. Okay, so it doesn't have to be done in the same order that we did the first time, where we put the concentration first and then multiplied by the rate. You could do the rates first like we did this time. And it's just because, the only reason I did it that way is because they gave us the rates first. Okay, as far as the concentrations, we're told the concentration coming in is 2 plus sine 2t grams per gallon. We want grams per gallon. Oh, that's perfect. Just pop that in. So we're going to have 2 plus sine 2t Could have given myself a little more space there. And then to figure out what the concentration is that's flowing out, the rate out, all right, we can do something similar to that we did last time. So we need grams, and so we need the total grams that's in the tank at any given time. Well, that's given by Q of T. So just put Q for that. And then how many gallons are in the tank, right? So pond initially, oh, sorry, a pond, not a tank, but initially contains 10 million gallons. And so we want 10 million here, 10 times 10 to the sixth gallons. And so that will give us the concentration of the undesirable chemical. We have Q, which is the amount of chemical, divided by the total number of gallons. And unlike in the example we just talked about where the rates differ, the rates are the same. We have 5 million coming in and 5 million going out. So that means that the number of gallons is going to stay the same, right? So if you start with 10 million, you'll continue to have 10 million if the amount of liquid coming in and the amount of liquid going out stay the same. Okay. And then so you could go through and maybe simplify this. The gallons cancel, gallons cancel. This is going to reduce, right? The 10 to the 6th cancel. And so we'll end up with 5 times 10 to the 6th. Let's just put some parentheses around that. Times 2 plus 2 sine 2. I did it again. I desperately want to put the 2 in front of the sign. Right? And then minus the 5 over 10 is going to reduce, and we get 1/2 Q. And there's our differential equation. dq dt equals 5 times 10 to the 6th times 2 plus sine 2t minus 1/2 Q. All right, so let's see if we can go through and solve that. Let's just copy it over to the next page. Okay, so we cannot go through and solve this problem using the same formula that we did on the last problem. The formula for the last problem specified that you had to have a constant here and a constant here. Right, let's just go back and take a look. Okay, this formula, to use this, you have to have a constant times the function you're trying to find, the variable, minus another constant. You need to have constants both here and here. We do not have that. All right, so this is not a constant. As a result, we can't use that method. Instead, what we can do is we can go through and use the method for solving a linear, this is a linear first order differential equation. How can we tell that it's linear? You can tell that it's linear because the dq dt is to the first power and the q is to the first power. That tells us that it's linear. And so we can use our technique for linear, which we covered in a previous video. That technique is the integrating factors technique. And with that problem, you move the dq dt and the q to the same side. And rewrite it into this form, okay? And then from there, once you have it in this format, so from here, if you haven't watched that video, you're gonna have to go back and watch it, or if you don't remember. Next, you go through and you find the integrating factor, right? So this is gonna be P, and this whole thing is gonna be G in the formula. And so you're gonna have mu of T equals e to the integral of P dt. So this is e to the 1/2 t. And then once you have the integrating factor, you can actually jump right to the solution by using the formula. All right, so q is going to be 1 over e to the 1/2 t times the integral of e to the 1/2 t times g, which is this thing. Plus C. Okay. So the next step is to go through and integrate this. Oh, and we need a DT in there as well. Next step is to go through and perform the integration here. The easiest way to do it, you can take this 5 times 10 to the 6 and you can just pull it right out of there to simplify things. And we could pull it out and combine it with this, right? So we're going to have 5 times 10 to the 6. Let's just clean this up over e to the 1/2 t out front. And then we're going to have integral. And the other thing you can do is you can take this and you could distribute it. So we'd have 2e to the 1/2 t dt plus, let's create a second integral here. And then we're going to have e to the 1/2 t sine 2t dt. And then we can also go ahead and take the c here and distribute that out to get it out of there. And so we'll have plus c over e to the 1/2 t. And so that we end up with just needing to go through and find these two things. So we'll have 5 times 10 to the 6th e to the 1/2 t. Our antiderivative here is going to be, the antiderivative e to the 1/2 t is going to be another 2 e to the 1/2 t. So we're going to have with 4 e to the 1/2 t. And then for this guy here, I just cheated and went and looked up the formula. You can go through and integrate this by hand using a technique from Calc 2, right? The integration by parts. But for the sake of this, we're just going to cheat. So if you look up the formula, you'll get e to the 1/2 t over 1/4 plus 4. So the formula has you square this and you square this, and you put it in the denominator under the e to the 1/2 t, and then it's times 1/2 sine 2t minus 2 cosine 2t. So yeah, the formula, you take this, the exponent of e, and it goes here, and you take the multiple that's inside of the trig function, and it goes here, here, and here. And again, you could just look that formula up if you're curious. So this is 5 times 10 to the 6th over e to the 1/2 t. And then we're going to multiply by 4 e to the 1/2 t. E to the 1/2 t again. This is going to be 17/4 1/2 sine 2t minus 2 cosine 2t. Okay, at this point you could take this and multiply it, flip it, multiply it by these two just to kind of clean this up. We're going to get 5 times 10 to the 6th over e to the 1/2 t, 4 e to the 1/2 t. There should be a t there. E to the 1/2 t, right? And then what are we going to end up with here? So we're going to have 2/17 sine 2t minus 8/17 cosine 2t. Okay, almost there. So the next step, we can go through and we can take this e to the 1/2 t and we can distribute it through this parentheses, and it's going to cancel these, right? So you can take this, cancel that. Okay, and then let's see where that puts us, right? So Okay, so assuming copied that down correctly, right? So those cancel. We've got 4, 2/17 sine minus 8/17 cosine. 4, 2/17 minus 8/17. All right, looks good. And then the next step is to go through and solve for C. So we want to go ahead and plug in our initial condition. So what was our initial condition? Let's go back and take a look. Okay, suppose a pond initially contains 10 million gallons of fresh water. Fresh water, what does that mean in the context of this problem? Uh, it means that the undesirable chemical, there isn't any. All right, so this is saying that the amount of undesirable chemical at time 0 is 0. Okay, so that's going to be important to go through and solve for our constant. Okay, so q of 0, we're going to get 5 times 10 to the 6th. And then what do we get here? So we're going to have 4. And if you plug in 0, that kills that. Cosine is going to be 1, so we're going to get minus 8/17 plus c over e to the 1/2. Oop, hold on, not e to the 1/2, right? If you're plugging in 0, that's going to become 1. So we're just going to have plus c. And then q of 0, we're going to have 0. And then if we go through and simplify this, this is 68/17 minus 8. So we're going to have 60/17. And if we swing that over to the other side, that's going to turn into 300 times 10 to the 6th. 17ths equals c, and we make it negative. And then plug that back in, and you get q of t equals 5 times 10 to the 6th times 4 plus 2/17 sine 2t minus 8/17 cosine 2t minus 300 times 10 to the 6th 17ths e to the negative 1/2 t. So just go ahead and take this and rewrite it with a negative exponent instead. And you could take the 5 times 10 to the 6 and multiply it through if you wanted to make it so it all looked more similar. But that's the answer. So that's how we can go through and solve another problem. And it goes through and shows how to solve problems where we have a variable amount, a variable concentration that is coming into the tank. Okay, so I hope that you found that helpful. Thank you for watching, and I'll see you next time.